The study of objective functions in further maths expects that a student knows, first of all, how to create a feasible region. Now, if you don't know how to do that, I'd advise you to have a look at the previous video in this playlist that runs through feasible regions. Objective functions can be any type of function that asks you to maximize or maybe minimize some quality. For example, you might be asked to maximize profit, maybe minimize cost or waste, or something like that. If you were looking, for example, at an area, let's imagine we have some kind of rectangle that is dimensions y versus x. The objective function here could be the area, and you might be asked to maximize the area. Now we know the area is x times y. So what we would do is we would have a look at our feasible region in all the values that are permitted in this problem and find out which set of values gave x times y, or gave an area the highest possible number, and therefore maximized the area. We're going to have a look at the example we took a look at with feasible regions, but we're going to create an objective function and explore how we can find our maximum or our minimum. So here we have a feasible region. It's the region shaded in this light blue color. Generally, when we have an objective function, we're told what it is. So let's imagine in this system, we're told our objective function, let's call it C, is 2x plus y. Now, often an objective function, which will be given to us, will be found, or always it will be found either at a corner or along an edge. So now we're going to have a look and see whether this is found at a corner or an edge. And one way we can find out is by substituting corners. So let's have a look at that. I'm going to take this point here, 25 and 50. At 25 and 50, x equals 25 and y equals 50, which means my C, when I substitute my values in, will be 2 times 25 plus 50, which equals 100. So that's one value that I get at this point. Now I do have to remember that this point doesn't include the point 25, 50, but we're using it anyway in this example. Now let's imagine here I have a look at the point at 75 and 0. So at the point of 75 and 0, my x equals 75 and y equals 0, which means C, remember that's 2x plus y, that will equal 2 times 75 plus 0. So I'm going to rub out my x and y and substitute in. And that equals 150. So in this case, if I had a look at all of the other points as well, what I would do is I would find out that the highest value of C, substituting in any of these points, would be 150. So therefore, my objective function tells me that my best scenario is where x equals 75 and y equals 0. We've had a look at what happens when we want to maximize an objective function. Now let's have a look at the same objective function. So C is 2x plus y. But let's imagine we want to minimize it. Once again, we're going to go to our corner points and see which functions or which points give us now the smallest value for C. What I'm going to do is I'm going to head off over here. Let's have a look at this point. At 10 and 0, C will equal 2 times my x value, which is 10, plus my y value, which is 0, which is 20. Let's go to the next point. Over here, we've got 0 and 10. It's 0 and 10. C will equal 2 times my x value plus my y value, and that comes out to be 10. So this one's smaller. Let's have a look at another point, 0 and 50 for argument's sake. C will be 2 times the x value plus the y value, and that's 50. So that's not what we're looking for because it's not minimizing. And this one here is not the smallest. It looks like this is going to be the smallest one. We would generally go around and look at all the corner points, but I know from what I'm doing here that this 0, 10 is going to be the smallest point. So that's how we use the corners of an objective function to find out the maximum or the minimum. Our feasible region will give us all our intersection points, and they're the values we substitute in. Sometimes you might find that you have the same value for two different points. So let's have a quick look at how that might work. Let's imagine that our objective function, let's call it C again, is x plus y, and we want to minimize it. So it's similar to our last example, and we're probably going to be looking over the left-hand side or the bottom of this graph to find our points. If we substitute in the point at 10 and 0, then C will be my x value, which is 10, plus my y value, which is 0, and that'll be 10. Now let's have a look at the next point. 0 and 10. Well, C will be my x value, which is 0, plus my y value, which is 10, which is also 10. So these 2 points that are on two ends of the same line, which is this line here, are both giving us a value of 10, and that's the minimum value for this function. That means that every point on that line will give us a minimum value. Now, if every point on that line gives us the minimum value, then we have one more question to ask ourselves, and that is, do I need whole numbers only, or can I use any number? Now, an example where you might only be able to use whole numbers is if you have a number of items, a number of goals, a number of animals, something like that, where you really just can't chop them in half, then you can only use whole numbers. And in an example like this, your objective function is minimized when your values will be 0 and 10, then 1 and 9, 2 and 8, and so on along this line. If you can use any number at all, and it doesn't have to be whole, I'll write not whole, saying that that's not a constraint, it doesn't have to be whole, then anything along this line, and this line was x plus y equals 10, anything along that line will give you your minimized objective function. If you found this or any of my other videos helpful, please subscribe to my channel or like the video. Thanks.